Okay, in this movie, we want to derive Kepler's third law. We've already discussed what it is. It's that if it's the square of the periods of any two planets. So if I have the period, and the period is how much time it takes to go around. So we have like a sun. See, we have a sun here. Nice, pretty sun. And we have a planet out here, and it's orbiting like this. And then we have another planet a little maybe further out here, and it's orbiting around the sun. And the Kepler's third law, which is called the law of harmonies, is that if I take the period squared of one of the planets, so like this planet here, how long does it take for this planet to get all the way around one time? And I divide it by the period squared of the next planet. So I divide it by how long it takes this planet to get all the way around one time squared. That will be equal to the cubed ratio of the distances from the sun out to those planets. So it'd be R1 cubed over R2 cubed. So the squares of their periods is proportional to the cubes of their distances from the sun. And so if I know some of these data points, I can figure out what the distance from a planet is from the sun, or maybe how long it takes for the planet to get around the sun. We want to try to just prove this ratio. And because I think we have enough abilities to do that now, we're going to use two equations that you know of. The first one is the orbital period for a planet. And if you remember, that's the same thing as the pendulum equation. So we can have t equals 2 pi times the square root of, and when we're doing the pendulum, we put the length of the pendulum over gravity. But here, instead, we'll do the length is the distance from the sun out to this particular planet. So we're going to call that r over g, over the gravity of what the planet would be out there at that particular location. That's the first one we're going to use. And the second equation is Newton's universal law of attraction. So there's a force that exists between a planet and the sun. And if you remember, that force is a big G constant times the mass of one object, we'll call it the mass of the planet, times the mass of the other object, and that would be, like in this case, the mass of the sun, all over the distance between them squared, which of course we're saying is the r. So I could say over r squared. So what we're going to do is we're going to try to use these two equations to show this ratio is true. So what we're going to do on both of these is we're going to solve for gravity on both of these. So on this one, if I square both sides, t squared equals 4 pi squared times r over g, I'll get gravity equals 4 pi squared r over the period squared. Now this one's a little trickier here. If you remember, the force is actually the weight, or the force is what we consider to be the weight of the like one of the objects. Like if we're gonna say like what is the weight of the planet, well, the force would be the mass of that planet times gravity, whatever gravity is out there. That would be the force between the sun and the planet, and that, of course, equals big G, mass of the planet, mass of the sun, over the distance between them squared. And the mass of the planets will cancel out. So if I'm talking about just planets, all planets going around the sun here, I'm going to have an equation that says G equals big G, mass of the sun, or whatever we're going around. I mean, these could all be satellites. Both these could be used for satellites going around the Earth, too. So this big M could be the mass of the Earth or the mass of whatever we're orbiting around. So I'll leave the S off. This mass could be the mass of whatever we're orbiting around over r squared. And so what I can do is I can set both of these gravities here equal to each other. So I'm going to have 4 pi squared r over t squared equals big G, big M, over r squared. And you can see here that if I take the t squared up to the top side, I'll do that, running out of room here. We'll do that right over here. So if I'm going to take the t squared up to the top side, and I take this r down the bottom side, I'm going to get t squared over r cubed, which looks pretty familiar. And what do I leave on the other side? Well, if I take, leave the 4 pi squared over here, 4 pi squared, and then I divide it by big G and by the mass of the thing that we're orbiting, then you'll realize that this whole section over here is going to remain constant for any planet going around the sun or for any satellite going around the Earth. 4 pi squared is just numbers divided by G, which is just a number, divided by the mass of the thing that all these things are trying to orbit around, is going to be the same for all of these planets. So this ends up being, this ratio of the period squared over the r cubed of a given planet is going to be a constant that's the same for every single one of these planets. So that's how we can say that the period squared of one planet over r cubed of that same planet is going to be the same ratio for any of these other planets. See, I can take this r cubed here and put it down here, and take this t squared and put it up here, and you're going to get the period squared of a planet over its radius cubed equals the period squared of another planet over its radius cubed. And so we can show from these two equations here how we get Kepler's third law ratio. Hope that made a little bit of sense.